Just within 2 minutes, we will begin our session. Just I'm waiting to join the resource person. Good morning, Dr. Rakesh. Hello. Good morning, Dr. Rakesh, sir. Rakesh, sir. You are not audible. Can you unmute yourself? Yes. Good morning. Sir, you are not audible still.
Hello.
Yes.
My voice is audible?
Yes. Now it is audible, sir.
Okay.
Okay. So good morning, all. I welcome you all for the last day of the FDP, Essential Mathematics for Engineers and Researchers. And the speaker of today's first session, I will introduce him briefly. Dr. Rakesh Lakshmikant Das. Currently, he is working as a consultant and faculty for competitive exams like IELTS, TOEFL, PTE, GRE, GMAT, SAT, and English coaching. He has completed his PhD on operation research from SVNIT Surat in the year 2019. He is having more than 10 years of teaching experience. He has published 8 research papers as a first author. Also, he has published some book chapters. He has awarded with full-time institute research scholarship by Department of Applied Mathematics and Humanities, SVNIT Surat. He has received Young Scientist Award at 19th International Conference on International Academy of Physical Science during 17th 19th October 2016. Also, he has received Best Research Paper Presentation Award at 81st Annual Conference of the Indian Mathematical Society, a national level event held during 27th to 30th December 2015. Also, he has received Best Research Paper Presentation Award at Second International Conference on Information Technology and Applied Mathematics in the year 2019. So this is what the brief introduction of Dr. Rakesh. Now, I'm requesting him to begin with his session. Thank you.
Good morning to one and all the respected faculties, research scholars, and the students of the department. Myself, Dr. Rakesh Das. Initially, I would like to thank the organizers for providing me this opportunity to give a session on the remark of faculty development program, which has been conducted by Department of General Science and Engineering, SKN Singlet College of Engineering in Pandrapur. My topic is about inventory models. My topic is about inventory models with carbon emission in fuzzy environment under green policies. Recently, I have come across, like last year, I have submitted my thesis, and I was more inclined toward working in the field of carbon emission. So I have later on considered this as my area of research under the major operation research field in the field of mathematics. So I would like to begin with the session. This is a table of content that we are going to deal with the today's session. Initially, we will have some introduction, and after the introduction, you will have some models.
Excuse me, sir.
Yes.
Can you make full screen of your slides?
Yeah.
Yes, sir. Yes, sir. Yes, sir.
Okay. So first of all, I would like to start with the table of content. Maybe it was not visible earlier, so I would like to again brief about it. In our table of content, the session that we have, it will start with the introduction. Introduction regarding operation research, how we are dealing. Secondly, there are several different environments to which we can deal the operation research topic. So we will have certain parameters over there. And the reason why carbon emission is taking place nowadays. So we will discuss certain factors about it, that how in a small amount we are contributing a lot of things for our environment. So that will be there in the introduction. Then we have inventory models with carbon emission in fuzzy environment. Now, inventory models, there will be models which is based on production and consumption based models, and carbon emission is the main concern in our case right now. So we'll be specially prioritizing this aspect, and with the help of fuzzy environment. With the help of fuzzy environment, there will be stochastic deterministic environment, to which there will be cost minimization and profit maximization methods. So we will see that which kind of approaches we have utilized. There are fuzzy based approach, there are genetic algorithm based approach. So we will discuss in length, and then we have a conclusion in future work and the references. So I will start with the session. Introduction, like inventory. What is inventory in general? Anything that we have as a form of stock or a good, that can be known as inventory basically. Sorry. Inventories represents those items which are either stock for sale, or they are in the process of manufacturing, or they are in the form of materials which are yet to be utilized. Basically, the amount of stock that we have in the form of goods or materials, that is what we call it as an inventory. And there are certain models that we have worked out, out of which is EOQ model, economic order quantity model. Is the ideal order quantity a company should purchase for its inventory given a setup cost of production, a certain demand rate, and other variables. Economic order quantity happens in such a way that we have to make sure that the order has been given in such a way we are maintaining the minimum amount of quantity, and the purchasing as well as the setup cost in the production is maintained up to when the certain demand is required. Then EPQ, this is the difference difference between EOQ and EPQ. When it comes to EPQ, that is economical production quantity model, it basically defines a company or a retailer who would be ordering the total inventory cost by balancing the inventory holding cost and the average fixed ordering cost. So there's a difference between these two things. At one case, we used to find the cost minimization, and on the second case, we used to determine the profit maximization. So there's a difference between randomness and fuzziness. I guess that of us are knowing that there's a huge difference between guessing what is random and what is fuzzy in nature. Basically, fuzzy logic is mathematical technique that is quite unlike randomness. The fuzzy part refers to using ranges and degree of membership. When fuzzy membership is concerned, we used to see there are set of parameters like which has the membership function assigned to it. Even in details, if we go ahead, then we'll see the randomness comes from two values. Either it will be 0 or 1 in case of a crisp fuzzy. And the fuzzy theory set can be used in a wide range of domains in which information is incomplete or imprecise. Basically, if I say an example that it will rain tomorrow, so it may or may not rain tomorrow. So there's always a incomplete or vagueness in the nature. So such things we can consider in the form of fuzzy variables. These are some of the solution techniques that we have utilized for our models. Right? Classical techniques such as finding the first derivative and equating it to 0, and then again finding the second derivative and keeping it greater than 0 was the general sense of idea. Well, analytical solution basically help us to get an idea, but when we have large amount of data and we want to find out the solution about those particular values, then we used to assign certain models or calculation technique. So in that case, we are assigning crisp set, we are using fuzzy set, we are using rough set kind of things. And to come out from this uncertain environments, there are certain techniques like GRG technique, generalized reduced gradient technique. Basically, we have used Lingo software, to which the software itself works with a parenthesis of GRG technique, where they knows the basic variables, they knows the free variable and the solution that we want. So that is one of the best way to find out that which parameter is affecting and which time. And genetic algorithm, as we know very well, that it depends upon the sampling of genetic algorithm is basically depends upon the fitness function, and to which there are certain parameters that is affecting like crossover mutation, right? So we'll be seeing that in which parameters we are changing. Like the next one is genetic algorithm with varying population. So we are using the fitness function based on the fuzzy set. We will change the population, and accordingly we will solve the models. And there are fuzzy edge based and rough edge based model. These are techniques to solve genetic algorithm, modifying it basically, so that we will get the best offsprings out of parents. Then we have multi-objective genetic algorithm and rough age-based multi-objective genetic algorithm. Precisely in our case, we have used this FAGA in our case right now, and GRG technique. So we'll be showing that. Uh, just wanted to discuss the phases of operation research. As inventory model is an cumulative part of OR, so we have to understand that operation research plays a vital role. Operation research is nothing but a systematic approach to provide a better decision-making platform, which has 6 important steps. It is generally that we need to follow step-by-step procedures. And right from the first step, like we have to observe the problem environment. As far as applying a model is concerned, mathematical model into a real life problem, we have to make sure the amount of research, the observations, the data that we have to make sure that mathematical problem sequence we are assigning with the real life problem. And then after analyzing the problem, we have to define the problem. That comes as a step 2. Then step 3 would be something that we need to develop a model, a mathematical model that has been presented in the form of equations to which we can derive the input and output variable relationship. In this occasion, we can develop a mathematical model and we can develop all the steps accordingly. Then we will have to select appropriate data. There's a difference between real life based problem and mathematical based problem. So when we are applying mathematical problems, we have to make sure that there should be certain set of data which should imply based on the real characteristics of a real life problem, wherein some data that we are giving as an input is set with that. Then selecting an appropriate data input. In this step, selecting the appropriate input data makes a wider decision so that a company will come to know that at what particular scale that I need to pay for my company. So data are again very much important once the model is assigned. Then provide a solution and test reasonables. Once we go with the solution, then we used to keep on working with the simulation of the coding. And after certain trial and error, we come to a conclusion that this is the perfect set of data, or these are the finest solution that we have as per this model that can resembles the best characteristics for the real life based problem. So if the solution is not reasonable, the model behavior is not proper, update and modify the model. So we have to keep on updating the model. We have to certainly change some parameters, and that will eventually lead us to the closest possible path so that mathematical model can resemble the characteristics of real life based problem. And ultimately, once we are satisfied with the implementation part, then at the final step, we can go back to the previous step and we can keep on checking the issues if some things is coming out of there, and we can come out with a proper idea or not. So these are basically the 6 steps of operation research that an individual needs to make sure once they are applying for a mathematical model. So we're coming to the introduction of this thing. As you already saw that there were phases, and now we will be discussing different environments. But before discussing about the different environment as far as fuzzy parameters were concerned, I would like to discuss something which is the carbon emission or the carbon footprint, what we consider. Carbon footprints has historically been defined as a total set of greenhouse gas which are emissions caused by an organization, event, product, or a person. Something that leads to the detrimental consequences of our environment. That is how greenhouse gas emissions comes into play. It is probably an extension of the concept of ecological footprints developed by the ecologist William Rees at the University of British Columbia in early 90s. So basically, we'll be talking about the footprint concept, how it came into consideration of people, industry, and government, why we started working hard for the carbon emission that actually it is impacting our environment, and what are the necessary precautions one should take. So there are some sort of data that we have, which will help us to understand the nitty-gritty and the very basic things about the carbon emission. So what is carbon footprint? The total amount of greenhouse gases produced to directly and indirectly support human activities, usually expressed in equivalent terms of carbon dioxide. The carbon footprint is the sum of all the emissions of CO2 which were induced by your activities in a given time frame. Initially, the carbon footprints were considered directly, and the activities are basically carried by, unfortunately, by we humans. So it is affecting not only the lifestyle of human being, but it is overall affecting our environment as well. This carbon dioxide ultimately leads to various other parameters. Let us quickly see to a basic calculation. Let's suppose we have a fuel system to which we have petrol, gasoline, diesel, and oil heating. They are considered per unit as a liter, and CO2 emitted per unit is 2.3 kg, 2.3, 2.7, and 3 kg respectively for these 4 types of fuels. Now let's suppose if our car consumes 7.5 liter diesel per 100 kilometer, then a drive of 300 kilometer distance consumes 3 into 7.5. Naturally, that is 100. If it is 100 into 7.5, then its 3 times would be 300 kilometers. So that is 22.5 liter diesel, which adds 22.5 into 2.7 kg, that is 60.75 kg of carbon dioxide to our personal carbon footprint. That means, like, we can understand the difference that how we on a right from a very small note to a higher extent, how we are contributing to pollute this atmosphere. And below are some of the points. Each of these following activities adds 1 kg of CO2 to your personal carbon footprint. Let it be if we travel by a public transportation. Let it be if we drive a car at a distance of 6 kilometers, and the amount of consumption what we saw earlier. Then fly with a plane a distance of 2.2 kilometers. That is equivalent to this one. So operating your computer for 32 hours, that is again a way of consuming 1 kg of CO2. Then production of 5 plastic bags, and likewise. So these are the small things which happens in our daily course, and we somehow we are contributing in many different ways as far as carbon emission is concerned. What is GHG? Greenhouse gas are those that can absorb and emit infrared radiation. In order, the most abundant greenhouse gases in Earth's atmosphere are this. The maximum amount of contribution is given in this distribution, that is from water vapor to carbon dioxide to methane to ozone. This is how the contribution factor is affecting our human life. And there are other greenhouse gases which might be emitted as a result of your activities. Apart from carbon dioxide, there are other harmful gases which leads to global warming. That includes methane, and like the activities that is going on. So you can also observe the fact which happens in the combustion process of an engine, where we observe that in our PUC, what we used to check, or there we observe that there's hydrocarbons, nitrogen oxide, and carbon monoxide, and there's PM. So these are the factors which affects our pollution atmosphere a lot. So we have to consider why these greenhouse gases are being so abundantly used and it is affecting our lifestyle. This is a kind of calculator to which we can, so sorry, a little bit difficult. Carbon footprint calculator. In our household, let's suppose we are just one member, then we're utilizing 3 kilowatts of power, and then natural gases, heating oil, coal, LPG, propane, wooden pallets. So ultimately, you can observe that we are almost utilizing offset as in 3.53 metric tons of CO2. So indirectly, that is contributing to our atmosphere. And somehow there are some parameters while nowadays electric vehicles or vehicles based on solar has been coming into frame. So this is how our country or globally we are trying to eradicate this kind of carbon emission issues as far as traveling is concerned. So for some basic things, what we need to consider as far as staying in a college or for the students is concerned. How green is your college? Does the college have a recycling program for its waste, paper, cardboard, cans, and bottles? And we have to make sure that if the things which we are thinking about contributing, we should start from the place where we belong to. So this is one of the most important thing. And does the college have a policy to use recycled paper? Does the college seek to avoid the use of disposable paper, plastic, foam cups, and plates? It's a very small aspects, but it contributes on a macro level. Has the college eliminated the use of aerosol sprays and fire extinguishers that contain CFC? Does the college have an active policy and strategy to reduce its water consumption? Does the college use environmentally friendly cleaning liquids? There are other things like, does the college avoid the use of garden and household pesticides using environmentally friendly alternatives instead? Does the college have an active policy and strategy to reduce its energy consumption? Does the kitchen offer choice of healthy food and discourage students from eating junk food? So these are the kind of things that actually affects right from the college time, because awareness starts from the very small age, and right a student at the college understands a lot of things that they can be a responsible citizen. So we should start implementing these strategies so that we can avoid as much as carbon emission, and that leads to the GHG effect. Now we will talk about the different environments that we have utilized in our inventory models. Those are the examples of the time frame to which we can understand that what happens in our real life scenarios and how we are consuming this kind of things that is contributing in carbon emission. So these different environments, these parameters like demands, inventory cost, that is unit production, purchasing cost, setup cost, holding cost, shortage cost, transportation cost, and there are many parameters involved in this. And this system can be deterministic in nature or non-deterministic in nature. Something which is crisp and precise, and something which is imprecise and fuzzy or rough, random or fuzzy rough. That means there is uncertainty and vagueness, then that particular parameter would be non-deterministic in nature. But the one which is deterministic has to be crisp and precise. That is already known and aware. So the crisp environment is something that the deterministic and precisely defined system parameters, the resources from the environment as a crisp one. That will be either zero or one that is fixed. It won't be sailing in between. And the fuzzy environment. It is an environment in which all or some inventory parameters, resources, goals and objectives, etc., are imprecise and vague. Due to human perception process, it is uncertain in non-stochastic sense called fuzzy. So that the nature itself says that the fuzzy parameters for the quantities are characterized by membership function. And there are stochastic environment and the rough environment. In this environment, some of the parameters like lead time, demand, resources, inventory cost, everything that gets notified by probability distribution. So there is a difference between probability and deterministic, what we said earlier. So it all depends upon the nature and the demand or any function of a commodity in the society is uncertain, not precisely known, but some past data about it is available. So hence it is stochastic in nature. This is some repetition, but then rough environment. In this environment, some of the parameters like demand, coefficient, inventory cost, planning horizons, etc., and are rough in nature. So rough environment, that means there is some uncertainty and there's no fixed value for that. So that comes as in rough in nature. And fuzzy rough environment. Already we have a rough environment, but there are parameters again vague and uncertain. So on those parameters, if we consider, then it is an environment in which some of the parameters are fuzzy rough in nature. That is, a variable is measurable function from rough space to the set of fuzzy variables. More generally, a fuzzy rough variable is a rough variable taking fuzzy values. So we have to, when we solve these models, I will show you that what kind of fuzzy rough variables, fuzzy possibility sense, necessity sense we have considered, so that we can understand the difference, how we have to consider input values. The main objectives of the sessions are to broaden some inventory or the production inventory models for single or integrated system, that is supply chain control system in one of a kind varieties of uncertain environments with few innovative and realistic assumptions which are not taken into consideration so far. Then we will to regulate some present probabilistic or fuzzy programming technique and to expand solution techniques, as I already said those techniques earlier. As according to the requirements of model described, the models are solved by means of those methods. So, then to transform the uncertain models into the corresponding deterministic single or multi-objective issues. Like in any real life problems that we have, if we try to entertain those things into mathematical models, then there are some uncertain parameters or something that we need to correspond either in the form of multi-objective or in a single deterministic. Let's suppose if it is a single deterministic, then it may be in the form of cost minimization, let's suppose. Or if it is multi-objective, then we'll consider two parameters at the same time, cost minimization and profit maximization. So this is how multi-objective issues are considered to reveal extraordinary outcomes or relations of the model parameters and region variables through some numerical examples and carried out this sensitivity. We have considered some analytical models and then we have tried to solve with the programming languages that we have, and that is based on C programming, Mathematica, or even in Lingo. So we have solved those parameters over there. And then with this sensitivity analysis, we have come across some good values through which we can understand the nature of graph and the sensitivity of the models. Now let us come to the inventory models that we have actually. And it is inventory models with carbon emission in fuzzy environment, which is the root cause of our discussion today. And the models are typically based on this thing. So we will start with the first model and the introduction of it. For an EPQ model with selling price and carbon emission, keeping goods of products in the form of inventory are considered as an asset. It is required all the way in every places mentioned by Goel. So what happens when we visit a shop? Over there, we are already bound with the certain parameters over there. Let's suppose I have a budget constraint. And if I want to buy a toothpaste, I have a budget of 100 rupees. But when the product is not available over there, I should try to substitute it with some desired product which can be suitable with the requirement as well as with the pricing. So in this occasion, what happens? It is really a tragic moment for a customer if the stock is not available, right? So the priorities set by the customers go alike. He might move to another shop, or he might wait for the product, or he may switch to the alternative product. So when a customer is switching to the alternative product that satisfies the basic needs as far as quality, price, and demand is concerned, then this situation is known as product substitution. So we will be dealing with a lot of product substitution based on the demand function, where we can carry on the demand function in the form of selling price, quantity, quality, and carbon emission. Those things are there in our model. Further, based on price dependent demand, like Ling obtain results for degraded items using two warehouses inventory model. Then a new concept of advance payment was introduced by Mighty 2009. Is my guide actually, and is a paper we have considered, and we did a further work on that. Determine optimal order policy with selling price and uncertain lead time. That is, lead time is something that we have to wait for the product to enter again when the stock is finished. So if it is uncertain in nature, what happens in those occasions? So the paper was about it. The environmental concerns are becoming increasingly relevant for firms due to more stringent various rules and regulations on carbon particles imposed by government and growing customers' awareness in social welfare. So there are various ways that now this is the main thing, that carbon tax has been implemented by large number of countries. Some countries have introduced carbon cap and trade scheme for the industries. This is the best way where a country or the government policy can work in order to eradicate carbon emissions from the huge multinational companies or the industries who are contributing a lot in the terms of pollution. So by furnishing economic incentives to sustain with the reduction in economic pollutants, emission trading has been used to control pollution. This cap and trade system, that means industry would be provided a certain limit, that this is the final limit that you have as far as the pollution is concerned. The industry is crossing beyond that limit, then industry has to pay penalty for that. So over this occasion, we have introduced CAPE and trade scheme. Carbon expenses are fundamental in light of the fact that change of fossil powers concept vitality framework to dependence in light of vitality, effectiveness, renewable vitality, and feasible energies, which won't occur without carbon charges or assessments sending to the proper elegant ways. So carbon tax, there may be other type of tax that includes energy tax and fees and dividend. So once these things comes into play, then there are taxes which inculcates in the form of carbon emission. And those
fishermen கடல்ல பயணிக்கும் போது மகாவ் தான் வழிகாட்டியா பயன்படுத்துவாங்க. ரொம்பவே ஆச்சரியமான விஷயம் இது. அங்க மேல கொஞ்சம் பாரு.
Hello. Hello. May I continue? Hello. Hello. May I continue? Yes. So tax plays a vital role in allowing any individual to get the benefits via government. As tax slabs makes aware about the system in which the category our tax frame satisfies. In our present investigation, we have considered carbon tax similar to income tax in a system, namely incremental quantity tax. So we are using the joint multi-economical production quantity model, considering carbon emission and quantity as a decision variable. So let me show you the model quickly so that we can understand it easily. And the reason why we have considered IQT system is because IQT has a very stringent policies, and nowadays government this carbon emission based policies are deployed by government, and this hello. Yeah, so we are interested in portraying a carbon tax, that is IQT system in general. So we have considered a tax slab, and we will show you one demonstration which has been done by Prabhu Desai. Hello,
Yes, sir.
hello.
Yes, sir.
It should contain. I am getting a voice from someone. Hello,
Uh,
hello. Is it audible?
yes, sir. Yes, yes, you are audible, sir.
Okay, okay, so I will continue. Sorry for that. Okay, so this is basically the output table which we can see. On the left hand side, you can see a tax system which is based on the tax slab that we have in the form of income tax. So this was the tax slab which we are actually having, and this is a literature that was carried out. So what we did is the range of slabs in our income tax system. So 0 to 5 lakh, the numbers in lakh, those are the taxpayers. Percentage of taxpayers happens to be in maximum category, that was from 0 to 5 lakh, and followed by slowly the amount of income as it increases, the taxpayers ratio is actually decreasing. So we have considered this C1 and C2. These two are the different slabs of the incremental quantity tax, where we have defined the minimum and the maximum slab system of that particular range. And on the right hand side, you can observe CO2, ATP, and QI, that is, the carbon emission, annual total profit, and the quantity that has been calculated based on this system. The calculation I will show it later, but we have tried to implement an incremental quantity uh, tax system comparative to income tax model, right? So this is the base comparison over here, and you can see similarly, like income tax, we have found out the carbon tax and we have derived certain values. And this is the literature survey of our proposed models, the reference and the articles that we have utilized. I have just sorted out it on a very brief manner. So on the extreme left-hand side, you can find the authors with the year, what they have worked out with their models. So they have considered environment, some have considered environmental factors, some has not considered, some has considered unit production cost, some has again done the single or the multi-variable objective. That may be for cost minimization, profit maximization at the same time. Then there are methods of solution. Some did it analytically, some did with pattern search technique, some did with genetic algorithm. So the blue line, what you can see is the one which we have worked, that is our present model. We have worked with the environmental effect. We have considered the production rate dependent unit production cost. We have considered the single objective model. And the method of solution that we have used is FAGA, that is fuzzy age based genetic algorithm under incremental quantity tax system. So as far as summarizing this literature is concerned, what lacunas that we need to cover, that the researchers has about these parameters, and what different we did in our research can be inculcated or summated in these points. Summarizing the above mentioned literature, the systematic chronological developments in the related areas are present in table 2. These vacuums are promoted us to consider the model and to present a guideline for a firm. There were some parameters which other researchers has not considered, and we have tried to mold and we have tried to consider it in our model. So there are these lacunas which were not considered. That includes a production system producing quantities after the passage of some time from the occurrence of production and emitting carbon from the beginning is considered. I will derive the model to which you will see that the product is based on production consumption model. And in the demand function, we have determined the carbon point so that apart from this demand function, this can also be separately considered. A production system considering joint production for carbon emission and quantity. I will show you the demand function, how it is a joint function over there, and how these parameters as a multi-values we have considered. And these values are considered as the fuzzy budget constants. That means we have find the profit maximization. When it is a fuzzy budget constant, then we have find out the profit maximization. And when it is cost space budget constant, that means we have find the cost minimization. For a firm, a general algorithm is presented to decide with production policy for optimum profit considering all the available carbon rules and regulations of the worldwide countries. So we have defined an algorithm. If this procedure is not working, we should shift to another algorithm. Or if it is not working, we can shift to another one. So based on the profit, we have to consider the policies over here. And a heuristic optimization method has been introduced, that is FAGA, on the IQT system, and the profit function is considered. Behavior of system profit against carbon cost is graphically depicted. There we have some pictorial representation. We will show that. Then let's come to the model. The title of the model is Pricing and Carbon Emission Reductions for Substitutable Items in an EPQ model using GAVP. So that means a demand function is there, and that demand function is based on pricing and carbon emission. And as it is a multi-value items, then there will be substitutable among those values. And solving parameter would be GAVP, that is genetic algorithm with variable population. So let's quickly go with the model. This is the model which you can see. This is based on the production and consumption model. As the inventory increases, right, you can see that the production is increasing, and likewise the demand function is decreasing. So at the point 0 to T1, you can see the production is already done, and you can see that it is decreasing at the rate minus Ti. That means from the time interval from 0 to T1, our production has been already been consumed, and from T1 to capital T, that is the total time, we are just coming out with the demand function, and it is decreasing with the time. So this is an inventory model which has multiple items, and this Ki and the Di value. So the Di value, I will define it ahead. And secondly, this is the second model. Over here, the scenario is different. We have considered fuzzy age-based genetic algorithm, and the product demand function is based on quantity and carbon emitting. In this model, it was based on pricing and carbon emitting. Right. So there will be a difference in these two solutions. Even the parameters are different. So these are the assumptions. Multi-product economical production quantity model is considered, and there are where I equals to 1 or 2. That means you have considered two items, two substitutable items, which are depending on the prices in carbon emission jointly, or either two or these two separates. Their prices and carbon emission are assumed to be independent to each other. Right? This variables has to be considered systematically. The inventory in building up at the constant rate of Pi minus Di units per unit time during 0 to T1. That I already showed over here. That is building up from 0 to T1 at the rate of Pi minus Di. And the inventory system considers price and carbon emission dependent demand rate. Production rate is finite. That means we know about it. And unit production cost as well as setup cost is constant. These two parameters are also involved because as far as production is concerned, so definitely setup cost will be involved in that parameter. Then we have lead time is 0 and no shortages are allowed. As you can see the graph, there is no shortage. That means there is no value going beyond T1. That is on the lower part. Even after the capital T, that is from the complete cycle, there is no shortages, or there is the point about lead time. right? The no shortages or lead time is 0. That means once the product is completed, we have a cycle length from 0 to T, and our product gets completed between this cycle. So we don't need to wait for some another item. It is not going below T on the negative part, or a customer don't need to wait for that time. So when the customer is not waiting, then there is no lead time involved in that sense. So that is the assumption that we have considered. In fully substitution means the loss of customer for a product is equal to the gain for its competitor product. That I will explain it with the equation over here. So these are the notifications. The main decision variables are QI and SI, that is quantity produced for both the items, and selling price for both the items. These are basic symbols that we have considered. So you can already see there is holding cost, setup cost, production cost, average carbon emission cost, carbon tax, production rate, ATP, ASTP. So these are the notations that we have used. This is very important, the demand function. I need to explain it in more detail because everything happens with the demand function. Over here, we saw that it is simply Pi minus Di, but this Di's equation value is this: D10 minus D11 S1 plus D12 S2 minus L11 C021 and the second value. Over here, what we used to consider, as I said earlier, that when we need to set a demand function, we need to decrease our own profit and we have to increase the competitor's profit. So minus D11 to our own price and plus D12 to the competitor's price. That is how we have to define the demand function. Same happens with the carbon emission policy and its values. Decreasing our own value and increasing the competitor's value. This is how we have two different set of parameters as far as demand function is concerned. Right? We have certain conditions that di1 and di2 should be greater than 0. Likewise for the other parameters. Then we are right now considering the difference d11 minus d12 that is greater than 0 and del11 minus del12 that is greater than 0. This is inversely related to the degree of substitution. This is Io-dose relation, right? So this will happen with the analysis and the sensitivity of the model, where we will consider the difference among these two values of selling price as well as for carbon emission. So I will show you how this Io-dose comes into play and what is the difference between these two things. Right? This is the model and the basic solution. I have just written the final equations. We have not solved in the detail so that we can directly come to the point. So the solution of the above differential equations are average carbon emission cost for the ith product, that is holding cost, setup cost, and the production cost. When it comes to deal with the average total profit, then we will add the selling price minus this average carbon emission cost. So this equation SI minus PI into DI minus the above complete equation. So that will give us the average total profit for the ith product. Suppose we want to find out the average system total profit as we have denoted earlier. ASTP, these are the variables, that decision variables, selling price in terms of multi-variables, that is S1 and S2, and Q1 and Q2, that is quantity. So when we define this thing in a multi-parameters, so that this will be the equation. And this is the final equation in that case. So after solving this equation and coming out with a solution, this will be the final values for that. So based on this solution, we have find out the further parameters. To solve this analytical solution, we have modified the genetic algorithm, right? And we have used these parameters. Initially, we have set the counter over here. We have changed few parameters, that is mutation value, the maximum size, counter of T, that is starting value, right? Over here, we have already defined the initial population. That means the size of the population, the mutation value, right? So once we assign this thing, then we can find the maximum profit, then we can assign the maximum fitness, right? And we can put a certain incremental parameters in the equation itself. So this is where the maximum things will be happening, that there will be random, based on the random population, we'll be selecting two best parents, out of which there will be certain parameters, that is like a crossover mutation among those chromosomes, and we will have the best offspring out of it. So that is how this algorithm happens. Until and unless we are observing the best chromosomes, that is P of T, right? And if we are getting this value at a desirable rate, that is the average fitness value, which is close to the sample's value, then finally we will end the algorithm. Then determining of probability crossover, that is as far as those parents are concerned. So we have considered Xi and Xj, right? So we have considered two intervals out of it. And this interval is based on young, middle age, and old age group, right? And there will be possibility measures of fuzzy numbers, that is young, middle age, and the old age with respect to their age. Now, when it comes to apply with the membership function, I will explain it with the help of figure over here. Now you can see on this particular slide, slide number 42, on the left hand side, we have membership functions at age interval and membership function of crossover probabilities. Right? On the x-axis, you can define the values is given in the range of 0.24. Over here, the age distribution is given. And over there, the young on the y-axis particularly, you can find these three categories divide accordingly. Right? So this is how membership function we used to assign. And this is getting different values because these parameters help us to get the best crossover probability. Like explaining in this table below, you can see the table which over here we can see there's young, middle age, and old age people, right? From parent 1 and parent 2, what would be the best case scenario? Like suppose over here, if the parent is young and the parent 1 and parent 2, both of them are young, then the crossover probability would be low, right? Because both of them are young, so probability would be low. If it is middle age with the parent 2, and if it is about this medium over here, then medium, so the probability is medium again. So likewise, we can consider for old age group. If the parent comes in the category of old age group, then the probability over here is low, medium, and high accordingly. So we can select based on the parents that what would be the best probability for offsprings as far as crossover is concerned. If we feel that the probability is too high, then we can give those preference for the offsprings out of these two parents. This is basic output result of this model which we have solved analytically. These are the values based on product 1 and product 2 that we have multi-items. So these are respective cycle time. On this particular time, we have found that the selling price quantity, the demand, and the time interval T1. And this is that iodos that I was talking about. You can observe the difference, that is D11, D12, D21, D22. So D11 minus D122, that is DSP1. So this is a difference over here. Similarly, this difference is given over here. So the differences among these values that we have to show the maximum differences so that we can come with the closest optimum values. So on the optimum result size, we can find out annual total profits, selling price, quantity, carbon emission, and the demand function. Similarly, this was for the demand function, which was optimum values based on the first product. This is second product, similar parameters, and this is the average product, right? Average system total profit. So these values we can consider over here. So we have considered 15 best case scenarios. The maximum difference you can observe these parameters, like you can see there's a maximum difference among the responsiveness, right? With this maximum responses, we can observe this annual total profit is actually getting low. And when we have started decreasing the difference between D12, D11 and D22, D21, you can observe by the last point, right? The difference is just 1 on iodos. So we can observe the total profit has increased. So with these parameters, we can come to know that as the responsiveness among the products is less, that means the difference is less, then we can get more profit. And likewise, it matters with the rest of the parameters, that is selling price, quantity, carbon emission, and we can see that carbon emission ratio is decreasing over there, and the demand function. So these are the parameters that affects, and this average total profit happens to be the sum of the product one and two. So this is the difference how it happens. The more amount of differences that we have from the iodose values, the maximum profit we can gain out of it. Similarly, this happened for the case B, right? We have another set of parameters that we have calculated, and this is for case A and B. How come case A, B, and this goes? I will go just back. For us, case one is according to D1 equals to D11 S1 plus D12 S2. Case one is all about the only the parameters which is included in selling price. Case two is the only parameters which we don't need to consider the parameters of S1, S2. We just need to consider parameters of carbon emission. So that would be case two. And the complete equation one over here is case A plus B. That is the summation of original demand price plus selling price and the carbon emission. This total is case A plus B, this values. This is A plus B total values. And these are separate values. Case B is all about CO2 values, right? And case 1 is all about as the selling price values individually. So this is how these parameters we are calculating, and we have observed a very fine nature that comes with this 2D, 3D graph. This is ASTP against the quantities. We can observe a beautiful plot. With the help of Mathematica, we have solved this. This is the concativity of the 3D graph, which is like ASTP against Q1, Q2. Similarly, we have considered the parameters for selling price. This is the 2D graph, this is the 3D graph. The concativity of this model itself shows that how numerically our values are accurate, and the solution is getting so beautiful nature of the curve. Then we can consider the model 2. This model, the difference between this and the above model was this. Over here we are considering quantity and carbon emitting divisions. Previously it was selling price and carbon emitting divisions, right? Previously it was all about IQT system, which was based on FAGA approach, and over here it was simply a FAGA with a new approach over here. So similarly, again we will have some assumptions and notations. Like demand is continuous at a constant rate. During production run T1, the production item is continuous at a constant rate T. Like what we used to have, there is no lead time is zero, shortages are not allowed. So there are some parameters. Because we come to know with a solution that based on selling price and carbon emission, we can come to a conclusion. Likewise, we thought of going with a likewise we have come across another model, and this model was based on quantity and carbon emission. So similarly, based on the figure that we have already seen earlier, so that production runtime is again from 0 to T1, right? And as we saw earlier, that the rate of Ki and simultaneously inventories increases at the rate of Ki and simultaneously decreases at the rate of Di. So that is how Ki minus Di we used to write. And once the production is done, then the demand function decreases at the rate of Di. So thus the average total inventory cost for the model is again this ATC. Over here the production cost, the setup cost, and this is the holding cost. These three things in a total is the average total inventory cost. Now, as the fuzzy parameters are involved, then the values of setup cost, holding cost, and production cost, which has cape, this symbol is a cape to which we can define the fuzzy values over here. So to consider the fuzzy value, we have utilized the cost due to CE over here. The average total emission cost unit time per unit produced would be CS, H, and P, and these are the values for this. You might be seeing the equation as same, but these are fuzzy parameters we have considered. So there is a huge difference. So this is the tax system. Lambda 1, lambda 2, lambda 3, these are the form of penalties. And C1, C2, C3, C4, these are the permitted carbon ratios. That means CO2 in terms of quantity should come in this range of C1 and C2. If it is going beyond that, then there will be penalty in the form of lambda 2. If it is not satisfying, then it will pay again the penalty in the form of lambda 3. If it is again not coming, likewise, till the last approach, if industry is not able to maintain their carbon tax, then there will be penalties in the form of lambda 1, lambda 2, lambda 3, likewise. And if they are not able to maintain that range, like for the first C1 to C2, C2 to C3, then definitely there are detrimental consequences which our industry needs to face. So these are the carbon emission cost setup that we need to consider. Incremental quantity tax IQT system. So that system we have calculated and we have find out a solution for that. So this equation number 11 is our solution as of now. And then we have solved this solution in our programming language and we have come to a value based on that. So the objective of the product model was to choose an order quantity QI that maximizes the ATP, that is annual total profit. So we have to define the order quantity in such a way that our maximum profit we can get from it. So that equation can be derived from this. Again, you can observe the selling price, holding cost, setup cost, and the cost that was associated, that is ACEC, that is average carbon emission cost. So these parameters you already see. This another parameter is added from it. So that will be annual total profit for us. As I said, there are budget constraints involved. Earlier I said if it is about budget constant, then profit maximization would be involved. And if it is about the space constant, then cost minimization would be involved. So first set is about crisp budget constant. That is, we have to consider P1 Q1 plus P2 Q2, which is less than equals to B. That means we have to make sure that we need to select a budget B in such a way that values associated with Q1 and Q2 should be less than equal to that budget. Because we are using a fuzzy parameter, so maximum assignment of budget should be already considered. We have to assign that value. That the parameters of P1 plus Q1 plus P2 plus Q2 should not go beyond that. So we will initially define the crisp budget over here. And as far as the random budget is concerned, then there will be a possibility that probability would be derived in this condition. The model remains same as developed above, except the budget constant of the system. Here B is a random. This dash, what you can see, that is a random budget constant. For this type of model, we have imposed constant as this. So this is a possibility based probability. So in that case, the B random would be greater than equals to again P1 Q1 plus P2 Q. So again, we have to define a value, and this was possibly derived by Rao in the year 2009, where M of B and rho B, these are the expectations and the standard deviation of normal distribution. Random variable B, as we already said, and respectively pi of x that denotes the inverse function of standard normal distribution of standard normal value by this equation. So this equation, we have defined these values in the programming and then we have calculated accordingly. And then fuzzy budget. When the fuzzy budget is interpreted, right, the concept has reduced to two basic sets, that is possibility and necessity. So possibility value is given by this equation and necessity is given by this equation, right? When we are defining this possibility and necessity sense, then the degree of impreciseness increases. That means the fuzzy budget value would be going through in a triangular way, that is B1, B2 and B3, right? So as we were defining the membership function, over there the membership function keeps on increasing as the possibility and necessity sense keeps on working in the parameter. So in this case, we have considered the triangular fuzzy, that is B1, B2 and B3 over here, right? Then we have the fuzzy random budget constant, right? Again, previously it was budget constant, then it became random, and now it is fuzzy random budget constant. So now you can see the symbol of B dash, that means it was random. Then this symbol above is about fuzzy. So budget constant is now fuzzy random budget constant. So it stands for the relation which are interpreted in the setting of possibility and necessity theories. So the above constants again reduces to this sense. Previously it was budget, rough budget, then the possibility sense increase, possibility and necessity criteria increased. And in this criteria, again, we are introducing probability sets. And again, this value should be greater than equals to J1 and J2, which represents the imprecise and uncertainty due to randomness, respectively. So, left and right fuzzy random variables we used to consider in the fuzzy values. So again, we will define this equation in this way. We have solved this each and every values in our programming, and we have defined the values. So final equation goes in this way. This is again a rough budget constant. Now B budget constant was B, as we have denoted earlier. If it is rough, then this cape symbol would be there. So when B is rough in nature, the rough constant B would be again greater than equals to P1 Q1 plus P2 Q2. And if it reduces into a crisper form, then this complete P1 Q1 plus Q2 P2 Q2 can be defined in this equation. This is the long set of equation that we have, and it comes from this approach itself. So we have to keep on solving these values until and unless the final rough variables is assigned. And this confidence range will be defined, that is TR1 between 0 to 1. And the psi1 values again between 0 to 1. So in this case, the rough budget constant B is been again categorized into B1, B2, B3, B4. Previously, it were 3 possibilities. Now it is 4. So the confidence level, now we have to define accordingly. And this was about a rough budget constant. If we introduce fuzzy in that, then again, this is the fuzzy rough in nature, then possibility and necessities, and it again comes with the nature of fuzzy rough. So these are the equations that we have involved. This is the flow of the algorithm that we have defined. It might not be visible, so I will just show it and zoom it. The input parameters that we gave on genetic algorithm code with the modified values. So we started with the population size and we defined the generation. We took a maximum size of population size that was 200. We defined the mutation parameter, the proximity rate, that is 0.9. Then we have then calculated the population at the rate P of T. So we defined the fitness function over here, the same algorithm that we saw earlier, but then there's a difference between selecting the mutation and probability criteria. So if the BOS, right, the best offspring set is better than the known offspring, then it is fine. Then we will define that as a best offspring. But if it is not happening, then we will again restore this value and we will replace the old population by the new one. As we very well know that Charles Darwin, the genetic algorithm actually works with the Charles Darwin theory, that is survival of the fittest. The best parents we will have, the better the offspring will come out. So that happens in the cycle and it keeps on repeating, right? If the generation goes ahead, like if we have already gone with the best solution, then we will replace the old population by the new one. And if this generation is been satisfied with the maximum size, then we will increase the generation equals to generation plus 1. Because we want to come out with the ultimatum of better offspring, that is BOS. So this was that, and okay. So again, this fuzzy age-based system has been defined here. So you can see this same parameters, but this is more important. We have considered algorithm for the model objective evaluation. Now again, you can see that we have defined a loop over here, in which we have defined the population size that was the counter, it was about 0. That I already showed you in this algorithm over here. It was in this figure, right? So initially we have defined this generation size, then we have defined the maximum population size. So we have applied the loop over here, or condition. So this was the size, this was the maximum size, and the iteration counter, right? So QI value has to be assigned in such a way that we will be evaluating the carbon emission. As I said, that C1 and C2 are the two different range. Suppose if the value is not satisfied for the said this Q parameter, if not satisfied in this range, then this ACEC in the form of penalty, that is lambda, would be go in this case. If it is not coming in the range of C1 and C2, then else if it will go to C2 and C2. If it is not happening in this range, then it will go with the range of C3 and C4. Likewise. So this if-else condition over here justifies this thing until and unless the better value of quantity model for this evaluation procedure for carbon emission we are not getting. We have to keep on iterating. We have to keep on working with if-else condition, and ultimately we will get the ATP value, right? So industry need to understand the concept that which particular range of C1 and C2 or C to C3 would be better to understand this aspect. So I believe that a company get a good idea based on this, that on which particular range they need to work out, so that they need to pay a minimum penalty and they can do the maximum consumption of their product, whilst not disturbing our carbon cycle. The optimum results were based on these parameters, right? And the budget concept, as I already said, is involved. These are the corresponding values of D1, D2, K1, K2, likewise. And those corresponding values will be implementing to ATP, 1, ICT, Q1, Q2. Let me show you the values directly. So these are the optimum parameters we have calculated. I'm just zooming a little bit so that we will get to know the values more clearly. This on the extreme left side are the values which are based on the input parameters. And on the right hand side, you can see the optimum result. As we have the multifunction that we have defined this optimum result in two different segments. That is, this is the product based on the first item. These are the product which is based on the second item. And the annual total profit is the average of both of these items. Over here, you can see on the left hand side that we are giving the input parameters of D1, D2, right? The production rate, holding cost, and the selling price. So we have to make sure that the quantity and the amount of carbon emission that we are looking for in this model should be given from the prerequisite set of parameters. So for the first 1 to 10 values, what we observed is that we have increased the demand function and rest of the parameters. Right? When we have increased these values, we observe that the annual total profit, ITC, and Q1 CO2, everything is increasing. And when we saw the reverse case scenario from the values of 11 to 20, we started with the maximum range and we started slowly decreasing the values to the point of 10. So from 300 to 290, 280, likewise, every time we have decreased the value from parameters of 11 to 20. When we decrease the value, we observe that as far as decreasing the demand functions, input parameters, and rest of the parameters are concerned, then the values of optimum result is again decreasing. So this nature shows that the company or the industry has to understand the maximum amount of demand if they will be having. Obviously, the annual total profit will be maximum. And likewise, on the reverse case scenario, as the demand function is decreasing, then the annual total profit is decreasing as well. And so it happens with the rest of the parameters. And this is the case sensitivity we have to do as a researcher to understand the input parameters that we are giving. Is it going best with the model or not? Is it resembling the best characteristic of the real life problem or not? So that is how we need to input the values. The fuzzy values, this is very important, the table input values for the different time horizons. As I said that we have defined fuzzy parameters in the form of crisp, random, fuzzy, random, rough, and fuzzy rough. So these are the input parameters we gave. And we define this value B as in 1065.02. That is, this is the maximum value of B. Now onwards, you will see B1, B2, B3, B1, B2, B3, B4 for rough, for fuzzy, possibility and necessity, everything you will see which is less than the crisp value which we initially defined, that was P1, Q1 plus P2, Q2 should be less than equal to B. So this was the most important criteria. And this is how fuzzy values about these equations. These are the equations. For all these equations, we have defined these input parameters. Based on these input parameters, we got all these values that we were looking for. So these tables were not based on fuzzy in nature, but this table is based on fuzzy in nature. When it is fuzzy in nature, what are the possibility and necessity sets? When it is fuzzy in nature, considering the random part, what are these possibility and necessity condition? When it is rough in nature, then what is its condition? What is the condition when it is fuzzy, rough, and possibility and necessity in nature? So we observe there are different ways it is affecting. Like the maximum B is allotted here. For the fuzzy value, we are getting the maximum output of ATPs over here. And likewise, the values are decreasing as the possibilities or the vagueness or the roughness is increasing. The total profit and these things are decreasing. So we have to make sure the budget that we are assigned, if we are making these perfect assumptions of values, then a company will sustain the maximum policy of getting profited. And those values of Q1, Q2, you can see the maximum profit it has, the minimum Q1, Q2 it has, right? As the profit was decreasing, then the Q1 values, the Q1 over here, everything is increasing. So this shows that the more amount of fuzziness, whatever it is, if you consider budget constant over here, since any company, suppose they are working with a finance over here, they cannot set that this is the maximum budget we have. We can define a value. But when it comes to dealing with practical solution, there are many parameters it is affecting. Let's suppose earthquake, let's suppose any natural calamities, let's suppose the strikes of workers or anything. Right? If these things comes into frame, then that budget again goes into out of frame. So then we are defining these fuzzy values. Then what could be the possibility? What could be the necessity? So this is how we define it on the different time horizons. So this is the graph of this particular value, right? We have defined the annual total profit against the Q1. So the nature of the graph itself shows that when we have the maximum amount of values in annual total profit, the nature of this Q1 goes accordingly. Likewise for the second result. This is for the carbon emission, right, in terms of Q1 and Q2. So these are two basic graphs. I would like to conclude about this work, what we did, right? We have solved two models over here, right? The very first model, Model 1 was about the production cum sales of products, which was substitutable on the basis of price and carbon emission, and are considered in the optimal prices, carbon emission, and net effective demand are determined so that the total profit is maximum. As far as an individual is concerned, if a store owner wants to make a maximum profit, he has to make sure that he is satisfying with the demand, is satisfying with the needs of a customer. That includes the selling price or the viability of the product. So if this nitty and gritty of any product is entertained, then yes, definitely we can say that profit will be maximum. Then the second point is joint and separate effects of price and carbon emission. As I said, that we has case A, case B, case A plus B. That means on the case A, we had the demand which was based on selling price. Then on the case B, we had the demand which was based on carbon emission. And the third case, that was case A plus B, that was the joint effect of price and carbon emission. So in different parameters, we observe that what kind of global strategy a market needs to assign as far as different prices or the similar products of its concern. So if a company has its own firm and it also has a sister companies, they can understand the strategy on which occasion they should introduce a joint policy, on which occasion they should introduce a separate policy. So for this company, it is very much important. Therefore, nowadays, price of a product has only little variations. But within that variation, the effect of carbon emission for the product has to be improved for the existence or the top at the market. Thus, price and carbon emission of products may be considered as independent for substitution within. So, this goes in a reverse way, like we used to go for reverse psychology or the reverse engineering. if we work out parallelly together, how about getting the values separately and then analyzing it? So when we are doing this consideration independent, still we are observing that substitution is perfect. Like case A was perfect with the values, case B was individually perfect with its values, and case A plus B, reverse also it was going perfect. So a company can decide a strategy which one they should implement first. More precisely, these investigations will be helpful for the managers of stores or production cum sales companies where substitutable products are produced and sold. So there are some ideas which can be represented from this. These values. That is the first idea. Production, production cum sale of two substitutable products with. So sorry. Production comes sales of two substitutable products which can be incurred with the effect of carbon emission. Then sustainability of the product on the basis of selling price and carbon emissions separately and jointly. As we saw, A plus B. This work can be included further as far as reliability for the product process is concerned, and more substitutable products can be introduced. Like suppose we had selling price, quantity, we can go with the quality, we can go with the different production part. So there are various parameters that we can involve in our demand function as well. Then the supply chain system incorporating retailers and customers, new investigation can also be performed introducing price discount on the substitutable products. Like nowadays we can understand the scenario how market strategy is going on. The advertising of the product goes in such a way that the discount itself affects the product and the customers used to get over this just because there are fancy ways to introduce these things. So if you introduce the price discounts over here, then there will be more chance that customer will switch their priorities and they will select the one which you have already provided. Then further, the investigation proposed in Model 2 for carbon emission in fuzzy environment using EPQ model. Here is a production inventory model where production rate and ACEC are considered in the model formulation. So again, in this parameter, we have considered EPQ model, right? And with this formulation of ACEC, we have considered the carbon emission cost over here, right? So that algorithm we defined, and that algorithm gave an impression that a firm management for maximum profit, taking all the possible management decisions into consideration against different regulation was given. Even we portrayed a good example over here. What happens in the different kind of countries, we have started implementing carbon emission in our country lately, but in overseas in many other countries, they have worked with a lot of models. They have come approach with an approach which is implemented in UN also. So slowly and steadily, every country has started bothering about carbon emission. Moreover, these results will be helpful for manager again for the production cum sale companies, where the solution would be based on quantity against average total carbon emitted and total profit when it comes to ensure the reliability of the production process. Basically, the main aim was to apply a quick and worldwide strategy reaction that will be earnestly required to reduce greenhouse gas emission and mitigate the effects of climate change. There are many untold and uncanny repercussions if the need of this greenhouse gas emission is not entertained. So the talk must be revitalized towards embracing a multi-horizontally planned inconvenience of a carbon tax as an intense modern strategy. So these are some of the thoughts that we framed out based on the Model 2. A carbon tax administration keeps away from the issues identified with picking a benchmark in a price approach. The characteristic standard is a zero carbon tax defined and determined with IQT system. For an industry, it is very much important to understand on which protocol they have to work, what kind of campaign trade system they have to work on, and which strategy would be optimal for them. So if this kind of price-based system is introduced, then industry will realize that if they follow this protocol, they can come across with a zero carbon tax system as well. So this IQT framework will be smarter to adjust the composition of instability, which overruns the exploration of environmental change, right? because this incremental quantity tax is more important, we can have certain restrictions on emissions, and with the supplies of green gas emission, while the profit limits are related to the flow of emission. So these things are basically approaching to us, and I would say that if there is an instability, right, then there will be something which can lead to carbon emission more precisely. In a price-based carbon tax, the spectacular has a guaranteed long-term regulation to adjust to, and can likewise say something the cost included, right? When carbon tax includes price-based things, when an industry is not realizing that they are making maximum pollution, and if they have been heavily fined, right, so they can understand what kind of long-term regulations they need to adapt, and accordingly there will be change in the system. It can go above as an incentive for consumers and producers to more or more energy proficient products and items. The price-based approach as carbon tax makes it easier to implement such value-based global modifications than the amount-based approach. When the price is already defined and the the individual firm or the customer knows that this is how I need to play with the carbon taxes, then the implementation process becomes easy until and unless it is followed in a systematic way. So these are the references that we have for this particular presentations. And I would like to acknowledge Department of General Science and Engineering, SKN Sinhat College of Engineering, Pandharpur, for giving me this opportunity to deliver an expert session in a faculty development program, FDP, on essential mathematics for engineers and researchers. And thank you so much.
Okay. Now, participants, if you have any questions, you can ask now. If you do have any question, you can ask. So, well, I think no one have a question. So, on the behalf of SKN Sinhat College of Engineering, Pandharpur, I'm expressing my sincere thanks to Dr. Rakesh for his valuable and detailed presentation. Thank you, sir.
It's my pleasure. It's my pleasure for giving this opportunity. I will once again thanks the organizer, especially to you, Shivaji, sir, that you have coordinated for every small nitty-gritty stuff for which I have asked you. So it was highly a pleasure for me to give this presentation, and I feel so happy to present in front of you all. And apparently, I'm started working as a teaching assistant in my college, where I did my PhD and masters. So right now, I'm the teaching assistant at SPNIT. So that was my update, which was not provided to you. That it recently happened yesterday. So that was the last thing I would like to say. And thank you once again.
Okay, sir. Thank you. So with this, I'm concluding today's morning session. So as usual, we will begin our afternoon session at 3 p.m. sharp. So thanks one and all.
Okay. That's my pleasure.